Hello guys, can you hear me? Let me see if I can see and hear myself. Okay, I can. So, how is everything? As you know, today we're gonna talk about game theory and Grundy numbers. You can see that I updated the name of the topic stream since you asked that what is it about. It's about game theory. I'm gonna talk about all about game theory and Grundy numbers. So we're gonna see that what games are and how can we solve the problems which are related to games. And we're gonna talk about a very important topic in game theory, which are Grundy numbers. These are very important. By the end of this session, you will be completely familiar with all of them and you will be able to solve problems with them. So, if you are ready for it, we can start talking about that. Let me also update the stream in Codeforces as well. Yes. So, how familiar are the rest of you with game theory? I'm waiting a little bit till more people join and then we start. We can talk for maybe 1 or 2 minutes. And guys, I again invite all of you to join our Telegram channel, our community where we have votes on what the next topic streams are, etc. All the links are in the descriptions below. Let me share it in here as well. Let me share it in the chat as well. This is the link of the Telegram channel. And yeah, we plan to have a topic stream each week on a new topic. That's our goal. We had a pause, but now we started again. I wasn't busy, as I told you. I was in Iran. I went to Iran, to my country, for a month, so I was not available. I couldn't have streams from there. The internet connection is not very well. It's not like the US. So I couldn't do that in a month. And now that I'm back, we're gonna start again. And we plan to have a topic stream each week. And I'm gonna ask you guys in the Telegram channel that what topic do you want to talk about and do you want to cover in the topic stream. Jiang leader off again to LGM. I think it's very difficult to maintain a rating of 4,000. Yeah, it's definitely is. You only need to end up ranked first if you really want to get above 4,000 and stay there. I think even if you get ranked second, you will get a negative delta. Yes, and guys, I got a lot of messages about tutoring, etc. So I've added a website that you can if you want to have a one-on-one tutoring with me, you can just take a look at that website. But one-on-one tutoring is typically very expensive, etc. And I don't really recommend to everyone. And I try to have teach you the things in my YouTube channel and have the free stuff here. So you don't necessarily need that, but just in case, in order to answer your questions, in case you really want to have one-on-one tutoring, you can see that in the links below as well. Okay, so I think that now enough people have joined. So, are you ready to start? What did you think about course? I'm thinking about making the course. If you want, we can talk about it at the end of this topic stream as well. I'm thinking about making a course as well, and if you want, you can talk more about it at the end of this topic stream, and just tell me that what do you want it to be about, etc. We can talk more about it. I've put a vote on our Telegram channel too, but we can talk more about it here. The frequency of topic streams are once a week. I try to make sure that I really have it once a week from now on, now that I'm back. I really try to ensure that. I'm sorry that this gap has happened, but I try to ensure that right now we're gonna have it every day. I will schedule them so that I make sure that I'm gonna have them. They are supposed to be on Fridays, but now the plan is a bit ruined, but we will get back on track and we're gonna have it. I try to fix it on Fridays again, every Friday, so that we have this structure again. Okay guys, so without further ado, let's start talking about our topic today, game theory. So I kind of missed this topic streams as well. Thank God that we are having it again. So let's start talking about it. Well guys, first let's talk about what game theory even is. Game theory is a field that I personally really like as well. Game theory. I personally have 2 papers on game theory as well. I have 2 papers. I have 3 papers in total. 2 of them are about game theory. I can maybe show them to you very quickly as well. It's a very important topic in theory at all, theoretical computer science at all. Let me maybe show you that as well. I have right now these 3 papers. These 2 papers are about game theory. These 2, the first one and the third one. These 2 are published in 2024. So, and it is a very active field, and there are a lot of people who are working on it. This is a very active field in the field of theoretical computer science. It is so practical in Codeforces and competitive programming contests as well. There are a lot of beautiful problems about game theory. So you need to have good knowledge about what game theory is and how can you solve a problem with game theory. And especially, as I told you, there's a very famous topic, Grundy numbers in game theory, that they help us a lot to solve game theory problems. And we're going to get familiar with all of them today. So, game theory in general talks about a game that is typically between 2 players. It's typically between 2 players. And it just, you probably have seen such problems before. It says that 2 players play a game. If you participated in today's contest, you can see that's how the problems look like. It's like 2 players play a game, and it asks you if both players play optimally, who will win the game. So that's a game theory. That's a game theory problem. That's the structure of a game theory problem. So it's usually between 2 players. It's possible that it's between more players as well, but usually it's between 2 players, and it just asks you that who wins the game, the first player or the second player. And it typically is the players play alternatively. So first the first player, then second player, then again first player, then second player, and so on. So let's talk about an example of game theory. About your question, how to learn advanced topics in general, I will try to, as I said, I will try to have more topic streams and have a course as well. We will talk more about that later. Sure. So, to get back to what I was saying, let's talk about an example of game theory and a game theory problem. So, for example, we assume that we have a game like this. Assume that we have a graph, for example, and there is a piece of stone on one of the vertices. So let's say that we have this graph. I mean, this graph, even if you are not familiar with graph, you don't really need to be familiar with graphs to understand what I'm saying here. So I will tell you that just exactly what it is. Just assume that we have a directed graph. It means that we have several vertices, several points, and several directed edges. And assume that there are 2 players playing a game, there is initially a piece here, or there is a piece here, and these two players play. And in each turn, let's say that we have more edges. Let's add several more edges as well. In this game, each player in his or her own turn can move this piece along one of the outgoing edges of that vertex. Okay, each player in his or her own turn can move this piece through one of these outgoing edges. For example, the first player can move the piece to here, and then the second player can move it here. Then the third player can move it, for example, here. Then what I said third player, the first player again. And then the second player can move it here. And then again the first player can move it here. The player who cannot make a move, the first time that a player cannot make a move, he will lose the game. So the loser is the player who cannot make a move. So it means that we are in this last vertex and then we cannot make a move. So even if you're not familiar with graphs, you understand this, right? There are several points and there are some arrows between them. You start from one of them. Each player can move it along one of these arrows, which are called edges. And the first player who cannot make a move will lose the game. You have to say that if both players play optimally, who will win the game? So the first question is that, this is an example of a game theory problem. This is the first problem that we're going to solve today. So what do you think? How can we solve such a problem? How can we solve such a problem if we have one piece in here and we want to, the two players are playing, each of them move them step by step, and the player who cannot make a move will lose the game. I want to hear your ideas. Let me bring laptop's screen. So what do you think we can do? Just let's brainstorm and talk about different ideas. Color the graph. What do you mean? How should we color the graph? So one idea is coloring the graph, and I want you to explain in more detail that's what coloring is and how do you mean to color it. BFS. One moment, let me think. Okay, you can think. Find out winning or losing state for each node. That's an interesting idea. Can you explain it more, Vegeta? Min and max. Topo search and then DP. Well, for now, I'm just talking about this specific game. Assume that we have exactly this graph. So don't think very hard, like we have a general graph and we have to provide an algorithm. Just first of all, assume that we have this own graph. I want to give you some time to find out if in this game the first player will win or the second player will win. Assume that the game is exactly this. I want you to tell me if the first player will win the game or the second player will win the game on this graph. Just give me one answer, first or second. These were good ideas that he said. Now, see that how can you apply it here in this example. Does the first player win or does the second player win? If we have odd edge, then first player win, otherwise second. Maybe search through all passes and record the number of moves of all, and on the basis of odd and even we get the answer. But what if we have both odd length passes and even length passes? Color with respect to BFS distance, odd or even, and check all nodes without degree 0. First will win. First. Bipartite is not necessarily bipartite. It's a directed graph. So if you want, do you want to turn it to a bipartite graph, or first player can force an even length pass? So there are 3 people who say that the first player will win the game. What do the rest of you think? If you just want to give me first or second, let me bring here. I hope that you've seen that what the graph looks like. So we have 3 people who have said the first player will win the game. Let's see. Well, you gave me good ideas about how to solve the problem. Well, a good idea, if we take a look at this graph, that was a very good idea to see that instead of just having DP mindsets. In here, I really want to recommend you to see DP topic stream as well. You can see all the topic streams, the link to the all topic streams here. This is also in the descriptions as well. You can see the all of the topic streams in this link. I really recommend you to watch that dynamic programming topic stream as well. So we can have this DP mindset, dynamic programming mindsets, and say that let's, instead of trying to find out who will win the game if we start from here, if the piece is initially here, let's solve it for each of the vertices. For each vertex, assume that we start from that vertex. We want to say that if we start from that vertex, does the first player win or does the second player win? So we want, for each vertex, we want to find out that if we start from that vertex, if the game starts from that vertex, does the first player win or does the second player win? Okay, so that's the point. So let's start from this last vertex. With this DP mindset, we have to start from the end. So assume that the game starts here. Does the first player win or does the first player lose if we start from here? If we start from this last vertex. If the game starts from this last vertex, does the first player win or lose? This is not a problem in Codeforces. I'm just saying this problem here. It's a theoretical problem that I'm saying here. Lose, yeah, exactly. The first player will lose because he cannot make a move. So this is a lose state. If we start from here, we will lose. The answer of the DP of this vertex, for example, is lose. So that's a lose state. Now assume that we start from here. Do we win or do we lose? I mean, if the game starts from this vertex, does the first player win, the player who can make the move win, or does he lose? Win. Exactly. He will win because he can just simply move to here. So if we start from this, it was better to first solve it for this vertex though, because this one has an edge to this one, so it was better to talk about this one. But this one is the same as well. This one also is a win state. So both of them are win states. Then what about this one? What can we say about this vertex? Is it a win vertex or is it a lose vertex? If we start the game from that vertex, do we win the game or do we lose? Exactly, we lose. But why? What is the proof that we will lose? If we start from this vertex, assuming that we're the first player, do we win the game or do we lose the game? And why? Lose, as all transitions lead to opponent winning. Yeah, that was a very good and beautiful argument. Exactly. So we will lose because all the transitions lead to opponents winning. Our opponent will win whatever we do. If you take a look at it, we either go here. I think I again made a mistake. I had to first, the way that I draw the edges is very confusing. So I had to first talk about this one. Sorry, I'm talking about this one first, because this one has an edge to this one. First we want to talk about this one. Is this one win or lose? Well, the point is that this one is a lose vertex. Why? Because if you see its outgoing edges, assuming that, for example, assume that it has an edge to this one as well. Okay. And we assume that in our graph, we are assuming our graph is in a way that we do not have a circle. We do not have a cycle. If you have a cycle, the game might continue indefinitely. So we should not have a cycle. So it's called, in a graph theory, we call these graphs DAGs, directed acyclic graphs, so that we make sure that the game ends. But anyway, I'm saying that this state is a lose state because whatever we do, we're gonna go to a state that our opponent will win the game. I mean, because afterwards, the game is either here or here, and our opponent is gonna start the game from that vertex. And we know that in both of the cases, our opponent will win the game. So whatever we do, we will lose the game, because whatever we do, our opponent is gonna be in a state that he can win the game. So if we start from this state, we're gonna lose the game. Okay? Yeah. Yes, none of us noticed it. Yeah, what was my fault? Yeah, so now what about the next vertex? Now what about the vertex that I was talking about before? What about, oh my god, what about this one? And so I was learning numbers and saw you arrive here. Thank you for your great teaching. Thank you very much, Shivam. It means a lot. Thank you. I hope that it helps you. Win because we can push our opponent to a losing state. Exactly. It's a win because we can push our opponent to a losing state. Exactly. Yes, we can send opponent to lose. That's a very good way of looking at it. These are very good ways of looking at it. So the point is that starting from here, we can move our opponent here. We can move the piece to this vertex starting from here. You know, I want to erase this. Starting from this green vertex now, we can move to here, and then our opponent is gonna start the game from there, and he's gonna start from a losing state. So he's gonna lose the game. So we will win the game. So this is a win state. Again, we can continue this. Again, let's make sure that we don't make any issues here. Starting from here now. Do we win the game or do we lose the game? It's again kind of simple. It's very similar to the ones that we solved. Starting from here, do we win or do we lose? Win again with the same logic, exactly. Again, we can send our opponent to this losing state. Now, starting from here, do we win or lose? Starting from this vertex, do we win or do we lose? Exactly, we will lose the game. We will lose the game. Because all our outgoing edges are to wins. So now starting from this vertex, do we win or lose? The start vertex, which is the real answer to the problem, we will win because we can send our opponent to a losing state. So the answer to this one is that the first player answer is that the first player will win the game. Will win the game. So yes, this is how we can solve it. We used some DP mindset, and starting from the end, we just could mark all the vertices with win or lose, and then we could find that if starting from the first vertex, do we win or do we lose. This is also a very helpful way of looking at game theory problems. It's about classifying the states as winning states and losing states. So we have winning states and we have losing states. So what are the conditions for winning states and losing states? Let's take a look at what exactly they were. It's exactly the things that we said. About winning states are the states that we are able to somehow go to a losing state starting from them. So win state is a state that is starting from that we can go to a lose state. Probably the rest of them are win as well, but we need to have at least one losing vertex, at least one losing state in the outgoing edges of this vertex. We must have at least one lose in outgoing edges. But what is a loser state? A loser state is in a way that all its outgoing edges are to the states which are winning states. Then we can do nothing. Whatever we do in the next turn, our opponent is in a win state, so he is able to win. So we can do nothing. So if all our outgoing edges are win, we're gonna be lose. If at least one of our outgoing edges is lose, we're gonna win. So if all are win, we're gonna lose. If at least one is lose, we can push our opponent to that loser state. Then we put our opponent in a losing state, in a state that he's gonna lose. Again, in the next turn, he has to move to a win state. So again, we are in a win state. So in this case, we will win. And that's how we can define losing states and winning states. And if you know this concept, you can solve these problems like this. You start writing winning states and losing states and simply find the answer. If we had more time, I would draw another example and I would ask you if that is a win state or winning game. I mean, does the first player win or does the second player win? But for now, it's just enough to just consider this example. You can draw an example for yourself later and see that how it works. But the point that you should not forget is that these win state and loser states are talking about the player who starts the game from that vertex. So we're saying that if a player starts from this vertex, who's gonna win? The one who started is gonna win, or is he gonna lose? If that person wins, we're gonna write win. If the opponent will win, we're gonna write lose because this person loses. So that's how we can find that out. So did you completely understand this concept of winning states and losing states? If you understood it, put a plus in the chat or use this 100 emoji. If it is clear for you, we can move on to the next thing. Can we do it iteratively here as order is not defined? Well, in a general problem, if you're given a big graph, it's good to, as you suggested, do a topological sort and start from the end, so that before each vertex, all its outgoing edges are, before each state, all its outgoing states are defined first. Their answer is defined. So it's better to do that. Otherwise, you can do DP many times as well, but your time complexity would be worse. It's better if you sort the vertices, if you're given a large n and you have to compute it. If you're given, for example, so what I'm saying, only for people who are familiar with it. So great, it seems like you understood it, that's nice. So I'm saying that if n was large, for the ones who know what topological sort is, for example, if you're given n up to 10 to the power of 5 and m, the number of edges also up to 10 to the power of 5, you first need to do a topological sort and then start from the end, from the sinks, and go back. If the vertex has, you can for each vertex, you can first set its state to a losing state and then have a for in all outgoing edges of it. If you find the lose in the outgoing edges, you will change it to win. Otherwise, you keep it as lose. And then all the states will be declared, their answers will be declared, and we can at the end say that who will win the game. Okay, so that's how we can solve it if n was large. You had a problem that n was large. Okay, so now let's move on to the next thing. Let's talk about another game, another example of game theory and what can we do and how can we solve it. Assume that we have a pile of stones and there are two players playing. So there is a pile of stones and there are two players playing. Each player in his own turn can remove 1 or 2 or 3 stones from this pile. You have to say that who will win the game. If both players are optimum, the player who cannot make a move loses. Can you write the code as well? It's better if we don't, because it's not the topic. I mean, this is just something that I said very quickly for the ones who are okay with that, but it's not very important at all. I mean, the main thing that I wanted you to get familiar with was this winning state and losing state. That was the main thing that I was looking for. So getting back to this, each player can remove 1 or 2 or 3 stones. Definitely we should have those many stones. For example, if we have only 2 stones, we cannot remove 3. But as long as we can remove up to 3 stones. We cannot remove more than 3. You have to say that if both players play optimally, who will win the game? And like before, the player who cannot make a move will lose. So assume that initially, in here we have 6. Assume that initially, for example, we have, let's say that we have these 6 stones. Let's say that we start from 6 stones. Do we think that the first player will win the game? Or do you think that the second player will win the game? So each player in his own turn can remove up to 3 stones from this pile. The player who cannot make a move, it means that when we do not have any stones left, then he cannot do anything, cannot remove anything. Who will win he will lose the game. You have to say that who will win the game if both players play optimally. Assuming that initially we have 6 stones in the pile. So you can talk about your ideas. First player wins. DP or pattern mode 3, that's very good. DP solution iterate from 1 to n. First player will win, he takes 2 stones, lose. First player will win, first player will lose. What do the rest of you think? So far we have both answers. Can we mimic this problem as previous one? That's something that we can think about. For DP of I, check for states DP at DP of I-1, I-2, and I-3. First wins. Yeah, that's a good idea. Let's first start with this DP mindset. And see that's how it goes. So again, we can define a DP and we can say that if we start, it's very similar to the previous problem. If you want to make it similar to the previous problem, it's similar DP. We say that instead of just solving it for 6, we will solve it for any number from 1 to 6. And we say that we want to try to solve DP of I. DP of I says that if we start from I, does the first player win or lose? So our answer is DP of 6. If DP of 6 is win, the first player will win. If DP of 6 is lose, the second player will win. The first player will lose. So let's start from the beginning. These are we want to see that what are the DPs. So let's draw a line here for 0, for 1, let's make more space, 2, 3, 4, and 5, and 6. First, for 0, is 0 a win state or a lose state? Do we win if we start from 0 or do we lose? First, just about 0. Do we win or do we lose the game if we start from 0? We will lose, exactly, because we cannot do anything. What about 1? Do we win or do we lose if we start from 1? We will win. Exactly, we will win. What about 2? Two is still win because we can again. It's like, you know, from 2 we have an edge to 1. We can make our next state can be 1, and also our next state can be 0. So we have an edge to a loser state, which is 0. If we go to 0, our opponent is in a loser state, so we will lose the game. What about 3? About 3, again, we can say that we have an edge to 2, we have an edge to 1, and we have an edge to 0, and 0 is a loser state, so we will win. We can go to 0 and put our opponent in a losing state. But what about 4? Do we win the game if we start from 4, or do we lose the game if we start from 4? We will lose, exactly, because all our outgoing edges are to win states, so we will lose the game. And again, about 5, we have an edge to a lose state. We have an edge to this 4, so we will win the game. From 6 also, because we have edge to 5 and 4 and 3, then we have an edge to 4, so we can win the game by going to 4, and 6 is also win state. So if we start from 6 stones, the first player is gonna win the game. But yeah, this TP will work, and if you are given some random n, some number n, for example, up to 10 to the 6, we are solving it in O of n. But can we also solve this problem for n up to 10 to the power of 18? Can we also be able to solve this problem for up to n to the 10 to the power of 18? Why 0 is loose? Well, because if you start from 0 stones, you cannot make a move. So we will lose the game in the first turn. In the first turn, you cannot make a move. And by definition, when you cannot make a move, you will lose. So if we start from 0, we cannot do anything, so we will lose. Not by this method. XOR trick. Actually, there is a pattern. Yes, that's a good thing. We can take a look at if we have a pattern or not. Yes. Some people are saying that there's some pattern when we consider the remainder by 4. Let's continue these values of these DPs and see if we can see a pattern. Let's consider 7 and 8 and 9 and 10 and 11 and 12. Well, 7 is again a win state because we can go to 4. But 8 is again a lose state because it can go to 5 and 6 and 7. 9 is in a win state because it can go to 8. 10 is a win state because it can go to 8. 11 is a win state because it can go to 8. But 12 is again a lose state because it can go to 9 and 10 and 11, which are winning states. So, what is the pattern that we can see here? Yes, we want to find a pattern, but we don't want to prove by AC. Although some people use that method as well, but we want to theoretically prove as well. But proving by AC sometimes works as well. So what is the pattern? 4n will lose, all other will win. Exactly. As many of you have said, if we can see that AC means accept. By accepting, we prove that, yeah, it's correct. So, yes, as you can see in here, if n modulo 4 is 0, we are in a lose state. Otherwise, if it's not 0, if it is greater than 0, we are in a win state. Let's say it's not 0. So we can just say that that's it. If n modulo 4 is 0, we are in a lose state. If it's not 0, we are in a win state. But now, how to prove it? We want to prove it as well. We want to see that what is the reason of it. That's some conjecture so far. We haven't proved anything. It just looks like that. It gives us this hint that probably it's related to modulo 4. But let's see if we can prove it as well. Well, what is the reason of it? Well, because if you start from 0, it's a lose state, right? Then the point is that the next 3 numbers can come to this state. So all of the next 3 numbers are going to be win states. But again, the number after that is going to have an edge to these 3 states, which all of them are win. So that one will lose the game. And this pattern will continue. Again, starting from here, the point is that when we have a lose state, that's what we are proving. If you have a lose state, the next 3 states are going to be win. And the next step, if I is lose, we are just proving that I plus 1, I plus 2, and I plus 3 are win. This is very easy to prove, right? Because all of them have edges to I. and I plus 4 is loose because its edges are to I plus 1, I plus 2, and I plus 3, and all of them are win. So this pattern will continue. I mean, again, starting from I plus 4, again, the same pattern will continue. There are 3 wins and then a lose. Then 3 wins, then a lose. Then 3 wins, then a lose. And this pattern will go on forever. So forever, we're going to have a lose and then 3 wins. Lose, 3 wins. Lose, 3 wins. Lose, 3 wins. And you can see that all the numbers modulo 4 will be lose, and all the rest of them are going to be win. So the point is that the distance between each lose to the next lose, we proved it. The distance between each lose and the next one is exactly 4, and the next one is exactly 4. So all the numbers which are modulo for 0, which are 0 modulo 4, are gonna be losses. There's also another way to prove it as well. There's also another way to prove it, and we can say that we can provide the strategy for the players. If n modulo 4 was 0, we can provide a strategy for the second player. How? We can say that whatever the first player chose, if the first player chooses k, subtracted the number of stones by k, in the next step you choose 4 minus k. For example, if you are the first player and you choose 1, in the next step I will choose 3. If you chose 2, I will choose 2. If you choose 3, I will choose 1. So after each 2 steps, the number of stones will be subtracted exactly by 4. Because n is a multiple of 4 from the beginning, I'm the one who makes it 0. Because always after your move, n is not gonna be divisible by 4. After my move, n is gonna be divisible by 4. So when the number of stones is 0, who has made it 0? You or I? I've made it 0 because I'm the one who makes it divisible by 4. After each 2 steps, the number of stones will be subtracted by 4. So I'm the one who's making the number of stones 0, not you. And you're gonna lose the game, right? So this is the strategy that I can provide for the second player if n modulo 4 is 0. And for the first player, if n modulo 4 is not 0, for the first player I can provide this strategy. I can just first say that first I choose n modulo 4. For example, if n modulo 4 was 2, first I will subtract it by 2, then n will be divisible by 2, and then it's like in this new game, I'm the second player, and then I applied the exact same strategy. So first, for example, if our number is 7 at the beginning, I will subtract it by 1, I will subtract it by 3, and then subtract it by 3, so it will be 4. Let's write it this way. I'm not writing it in a very good way. Let's subtract it by 3, so it will be 4, and then whatever you choose, I will choose 4 minus that. So I first subtract by n modulo 4, and then whatever you choose, I choose 4 minus that. So this is how we can say that we can just see that who will win the game. If if n modulo 4 is 0, the second player will win, otherwise the first player will win. Is it clear? If it is clear, again, please put a plus or use this emoji, this 100 emoji. Gennady Korotkevich. I'm just assuming that. Let's see. Yeah, this is the original tourist. Okay. So, is it clear for everyone? This is a stream on Codeforces, so I decided to watch it for some learning. Yeah. Okay. So that's how we can prove it. That's how we can prove that if n modulo 4 is 0, the second player will win the game, otherwise the first player will win the game. That's all about it. Okay. So, the next thing. I'm using freeform, I guess. Yeah. So, let's talk about the next thing. Now assume that in this game that we talked about at the beginning, instead of one stone, we have several stones. What can we say then? Assume that we have one stone here, two stones here, or two pieces here. As I said, I use terminology of pieces. 3 pieces here, and 1 piece here. 1 piece here. Then my question is that if each player can make it in his own turn, can choose one of these stones and move it by one of the edges, one of the outgoing edges, then who will win the game? It's fun how all game theory can be some form of DAG. Yes, it should be the DAG. The graph between the states should be a DAG, because it should not. Why should it not have cycle? Why is it directed? Because from this state you can go to this state. Maybe you can't go vice versa. You cannot go from that state to this one. And why it should be a cyclic? The reason is that if it is cyclic, maybe it will go on indefinitely. That's the point. Maybe it will go on indefinitely. So that's why it is some form of DAG. Tourist is among us. Yes, tourist is learning the topic. Didn't you know that? Okay, so what do you think? What idea do you think about? If each time we can just choose one of the pieces and move it along one of the edges, who will win the game? What do you think? Let's just brainstorm some ideas again. So I'm saying that if you have several stones, who can win the game? If a game has infinite being win for one of the gods, it's more difficult. Yeah, that's also possible. In some games it's like that, and it's not very difficult as well in those problems. We can talk about that as well in future. So this is when we need something more than win or lose, because now if you take a look at it, now just considering if a state is win or lose is not enough, because maybe, for example, this state is a win. Probably a state is a win, but we don't want to move it to a lose state. Maybe we want to move it to another win state. So it's also important if a win state has an edge to a win state or not. So it's like different win states have different shapes, and some of them have edges to different wins, some of them don't. And you know, it's like the win states are different to each other now. And we cannot say that we can use the terminology of win and loses anymore. I mean, we cannot use only the fact that if a state is win or lose, because we cannot. I mean, even though this one is a win, we cannot guarantee that if a player moves this, it will definitely move it to the lose state. Maybe it will move it to a win. He will move it to a win state. So, because now each turn they can choose one of them and move them along one of the edges, and the game ends when none of the pieces can be moved. So you want to make sure that you're not the one who in his turn you will not be able to make a move anymore. So it means that all the pieces are in the sync, are in the last vertex. Is it clear what I'm saying? Is it clear what the problem is and why winning or losing is not enough? Again, if it is clear, please put a plus or use this emoji. I will do contests of solving streams from now on. I will do it again. As I told you, I wasn't here. I wasn't in the US for a month. And now I'm back and I'm gonna start streaming the contests again. I streamed one contest last week and then I couldn't do the next two, but now I'm okay and I can start streaming again. Is it not clear? So basically what I'm saying is that starting from each vertex, the point is that we do not necessarily want to move from a win state to a lose state, because it's possible that we will move it to a win state and in total it's going to be helpful for us. Okay, so assume that let's talk about an example. Let me draw an example for you that can help you to clarify this and see that when do we not necessarily move from a win state to a lose state. Assume that our problem is like this. For example, this is our deck. So if we just think about one stone, having a one stone, you can see that this is a loser state, this is a winner state, and this is a winner state. But if you have a game that there's one stone in here and one stone in here, how does the first player play? The best move for the first player is to move this stone to here, and then the next time the second player will choose one of these two and the first player will choose the other one and he will win the game. So you see that sometimes we go from a winner state to another winner state. So only win or lose is not enough. This is the motivation to talk about this powerful tool that we're going to talk about, and it helps us to solve so many game theory problems. So let's talk about that. But in order to talk about that, first I want to talk about a famous game theory problem which is called Nim Game. Have you guys ever heard about Nim Game? It's a very famous game. So yeah, and the problem that I said is not necessarily depending on the parity of the number of winning stones. That's not about that as well. Yes, I can do with code contests as well. So let's talk about this Nim Game and see that what is it. In Nim Game, it says that you have several piles of stones. You have several piles. Each pile has some stones. For example, the first pile has A1 stones, the second pile has A2 stones, and so on. So it's like this. And there are two players who are playing. Each player in his own turn can choose one of the piles and remove several stones from that pile. A player who cannot make a move will lose the game. It means that if for a player all the piles are empty, then he cannot remove any stones from anywhere. So he will lose the game. You have to say that if both players play optimally, who will win the game. So I repeat the problem. It says that there are several piles of stones. For example, there are n piles of stones. In the first one, there are A1 stones. In the second one, there are A2 stones, A3, A4, and A5. Each player, there are two players who are playing. Each player, in his own turn, can choose one of the piles and remove several stones from it. Each player, in his own turn, can choose one of the piles and remove several stones. At least one stone. At least he has to remove at least one stone. A positive number of stones. And you have a player who cannot make a move will lose the game. You have to say that who will win the game if both players will play optimally. So I'm saying that in the comments some of you are talking about XOR and you have some ideas that it's about XOR. Well, It's not a bad idea, but let's say that how can we interpret it? Let's find the intuition behind that. Let's talk a little bit first on how this problem might be, how we might be able to solve this problem. First of all, for example, if you take a look at it, we see that we have two piles such that both of them have 3 stones. So the thing that I want to prove is that if we have 2 piles with the same number of stones, we can delete both of them, we can ignore both of them, and the answer to the problem will not change. So the answer to the problem, if we have this 5 pile of stones, or if we have only these 3 piles of stones, is not different. That's the thing. So I want to prove that first. If we have 2 piles of stones with the same number of stones in them, we can delete both of them and nothing will change. Okay. So how can I say that? And I can say that's very similar to this also in here, in this game. If there are 2 pieces on the same state, we can delete both and the answer will not change. If there are 2 stones, 2 pieces on the same vertex, we can remove them both and nothing will change. But why? Let's prove it. Let's first talk about in this example. Why does it happen in this example? Well, the point is that, assuming that if I delete these 2 stones, I'm the one who wins the game. I'm the first one, for example, and I'm the one who will win the game. I want to show that regardless of if I'm the first one or the second one, I'm showing that if without these 2 stones, I'm able to win this game. If you add these 2 stones as well, nothing will change and I'm still able to win the game. Why am I still able to win the game? Well, the point is, when you add these 2 pieces here, I can still assume that these 2 do not exist. I know that in the rest of the game, I'm the winner. I know that if I ignore these 2, I'm the winner. So I just keep ignoring these 2 and I assume that they do not exist at all. I don't do anything with them. I just play my strategy in the rest, and I know that I have a strategy to win with the rest of these pieces. So I do that strategy and I will assume that these 2 do not exist. Until my opponent, do a move on one of these stones. Until you do a move on one of these 2 pieces. Assuming that, for example, at some point you just move this one to here. Then I simply copy your move with the other piece. So my strategy, my augmented strategy in here is going to be like this. I assume that these 2 do not exist at all. Only in the turns that you move one of these, I will move the other one and copy your move. So it's like these 2 will have like their independent moves that I just copy that what you do on them. And in the rest of the game, I will win as well. So basically, I'm saying that by adding these 2, the winner does not change. Whoever who wins without these 2 will still win with these 2 as well, because he can just play with the rest of the pieces, and just when you add these 2 pieces, he can still ignore them. And whenever you played with one of them, he can play with the other one and do the same thing. Is it clear? If it's clear, please put a plus or use this emoji again. DP with graph. We can talk about the next stream. In the Telegram channel, if you join the Telegram channel, we can talk about it. You can find the link to the Telegram channel in the descriptions as well. I will put a vote for the next topic stream. So it's clear for tourists as well. Nice. Okay. Nice. So I'm saying that adding these 2 will not make a change. So I can just say that, yeah, I will talk about this. So I can just say that in this problem, I can just remove, if I had more than 2 pieces on a vertex, I can take it modulo 2. Only the parity of the number of stones on a single vertex matters. So I can delete these 2 as well two of these, I can say that these two can be removed. Adding these two or removing them does not make any change. So it's like this problem will turn into we have several stones on some of the vertex. Each vertex either has a stone or does not have any stones. It's only 0 or 1. It's not more than that. Exactly. Odd number of stones become 1. Even number of stones becomes 2. Okay. So let's talk about this, about here. Let's talk about this point. I am not the realtor. Thank you for clarifying it. Okay, so for here, let me change this. Let's get back to here. In here, I can just say the same thing. I can say that still, I can, if I have two piles of stones with the same number of stones, I can delete both. Why? Because still, assume that without them, I win the game. Assume that with just considering these ones, I will win the game. Now, if you add these two, I still can win the game. Why? Because again, I can assume that these two do not exist. Just whenever you make a move on one of these two, I copy your move on the other one. For example, if you delete 2 from this, I will delete 2 from this. So it's like I'm again making these two independent, an independent game that also in that I'm gonna win as well. Whenever you played on that one, I'm gonna make the last move on that one. And in the rest of the game, I will win as well. In the rest of the game also, I have a strategy. So my augmented strategy is gonna be like this. I'm gonna win the game on the rest of the piles. And when you add these two piles, I just when you played on one of them, I will play on the other one and do the same thing. So that's all. So again, I can remove two piles with the same number of stones. So as you said, yes, the solution to this problem, the solution to this problem is XOR. I mean, it uses XOR, but let's think about why. I mean, if you have some intuition about it. For example, what does XOR do? We know that if we have two piles with the same number of stones, when we XOR it twice, what is gonna happen? What is the effect of adding two piles with the same number of stones? If you add two piles with the same number of stones, it's like you're XORing it twice. So what's gonna happen when you XOR the same number twice? It's like you don't have it at all, right? When you XOR it twice, it's like yes, it's gonna be 0. If you XOR a number with itself, if you XOR it twice, it has no effect, so it's gonna be 0. Okay, so let's get back to here. I'm just saying that it also complies with this. I mean, I want something that, for example, I want my solution to take into account that if I have two piles of stones with the same number of stones, it will not affect my answer, for example. So now I want to prove that. If we had time, I would give you some additional time as well to think about it. But in here, I can also explain it. That's what can we do. Well, I want to say that if the XOR of all the AIs is 0, the second player will win the game. If it's not 0, or in other words, it's a loser state. If it's not 0, it's a win. It's a win game. The first player will win the game. So if the XOR of all the AIs is 0, the second player will win the game. If it's not 0, the first player will win the game. So that's what I want to prove here. So how do I prove that? Well, the point is that what did we say about losing states and winning states? It has two parts. We said that from a loser state, all the outgoing edges, all the outgoing states must be win. But about a win state, we said that a state is a win state if at least one of its outgoing states is a loser state. So if all the outgoing states are win, we're gonna lose in that state, otherwise we're gonna win. If there's at least one one outgoing lose state. Even if the rest of them are win, but if we just have one losing states, we can just go to there and force our opponent to lose the game. So we're gonna win the game this way. Okay, so how can we prove it here? Again, we have to prove the same way. I want to show that I have to shoot two things. I want to show that if the XOR is 0, the player, because it's a loser state, I have to show that all the outgoing states are gonna be win. Or in other words, I have to show that whatever I do after this step, my XOR is gonna be non-zero. So if I want to show that this is a loser state and this is a winner state, I have to show that if XOR is 0, then whatever I do, XOR should be non-zero afterwards. If the XOR is non-zero, I have to show that there is one move that makes the XOR 0. So basically, how can I prove this? How can I really prove that? The answer is this. We calculate the XOR. If it was 0, the second player will win, otherwise the first player will win. If I want to prove it, I have to prove two things. First of all, about the base case, I know that when all of them are 0, it's a loser state because I cannot make a move. So I'm gonna lose if at the beginning all of them are 0. So in my base case, XOR is 0 and that's a lose case. About the rest of the cases, I can say that I have to show that if the XOR is 0, all the outgoing states have XOR to be non-zero. If the XOR is non-zero, there is one way, there's at least one outgoing state, there's one state that I can go to where XOR is going to be 0 there. And then I can force my opponent to lose. If I prove this to them, it is proved that if XOR is 0, the second player will win, otherwise the first player will win. Do you guys agree with this? If you agree with this, again, please put a plus in the chat or just use the 100 emoji. And if you do not, ask me your questions or tell me to repeat it if you want. So all I'm saying is that in order to prove that this is true, I have to show that if XOR was 0, I have no choice by making the XOR non-zero. If the XOR was non-zero, I can somehow make the XOR 0. Well, if every game losing, then it's losing. But if there are 2 winning and rest are losing. No. I'm talking about the whole game. I'm not talking about just one pile. I'm just considering the whole game, all of the piles. And I'm saying that if the XOR of all of the piles is 0, then I'm gonna lose the game, otherwise I'm gonna win the game. The state is defined on all the piles. A state is a situation. The definition of a state is the situation that we're in right now. Okay, what's XOR? Yes, exactly. XOR is about binary numbers. I mean, for example, 5, if you write 5 in a binary way, it's gonna be 1, 0, 1 in base 2. And if you write, for example, 11 in base 2, it's gonna be 8 plus 3. So it's gonna be 1, 0, 1, 1 in base 2. So if you calculate XOR of 5 and 11, it's gonna be written like this. XOR is written like this. It's gonna be 1, 0, 1. I can add a leading 0 as well here. XOR 1, 0, 1, 1 in base 2, which is gonna be equal to, in XOR, you will consider bits by bits. If they were equal, you put a 0. If they were non-equal, you will put a 1. So in here, we see that these two are not equal, so I put a 1 here. These two are not equal, so I put a 1. The next two are not equal again, so I put a 1. The next two are equal, so I put a 0. This is in base 2, and this is going to be equal to 8 plus 4 plus 2, so it's going to be 14. 5 XOR 11 is going to be 14 then. And if you want to read more about XOR, I send you a link to the Wikipedia page, XOR or exclusive OR. You can read more about it here in this Wikipedia page. I will put it in the descriptions of this video as well. And bitwise XOR is also this. Is it clear? Yes, this is the bitwise XOR, yes. It's bit by bit, yes. So, okay, I put these links in the descriptions of this video as well. So I want to show that if the XOR is 0, the first player is gonna lose, otherwise the first player is gonna win. In order to do that, first I'm gonna show that if XOR is 0, I have no choice by making it non-zero. Why? Because if XOR is 0, I have to change some number. I have to pick some AI. And if it is right now equal to some X, I have to change it to some Y. So I have to change some X to some Y. So my XOR right now is 0. After this move, X will be removed. So in order to remove X, it's enough to XOR it with X so that X will be removed. And then Y will be added. So I have to XOR it with Y. So if my XOR right now is 0 and I change X to Y, my XOR from 0 will turn into X XOR Y. So, and because X and Y are not equal, X XOR Y is non-zero. So our XOR after this step is definitely gonna be non-zero. So I proved that if my XOR right now is 0, I have no choice by making it non-zero the next time. Okay. So if my XOR is 0 right now, I have no choice by making it non-zero the next time, because I have to change one number. And when you change a number, the XOR is not gonna remain the same. Your XOR is gonna be changed because you're changing one of the numbers. So if it's 0 right now, the next time it cannot be the same number. It will change and it's gonna be non-zero. Is it clear? So basically I'm saying that if XOR is 0 right now, you can't do anything and your XOR will be non-zero afterwards. Again, please, if it's clear, put a plus or use the 100 emoji again. Let me also move this to here so that I can continue this explanation in the same page. Okay. And if you had any questions or if you didn't understand, put a minus in the chats. Just let me know, I will explain it again. So if XOR is 0, the XOR will be turned to non-zero next time. Now I want to say that if the XOR is non-zero, I can somehow make it 0. If my XOR is non-zero, that's also something that I have to show. I have to show that from a win state. I showed that. I mean, it's like I'm using induction. I'm proving it inductively. I'm saying that, okay, I want to see if these are really lose states and these are really win states. I know that in the base case, when all of the numbers are 0, that's a lose case, and it's really in this part. XORs are 0. So that's really a lose case. Now I have to show the steps as well. I have to show that from one of these states, I have no choice by going to these states. And also from each of these states, I can go to at least one of these states, one of these lose states. So I have to show that from each of these lose states, I have to go to all of these win states. I mean, all of the outgoing states are win. From these win states, at least one of their outgoing states are lose. So now assume that XOR is not 0. I want to show that it's a win. I have to show that I can somehow change some number such that my XOR will be 0. Well, consider that the XOR of all the numbers, the XOR right now is some X. So assume that our XOR right now is some X, and X is non-zero. Well, how can I make the XOR 0? What's the operation to make the XOR 0? If my XOR right now is non-zero, what's the operation that I can do to make the XOR 0? When XOR is 0, when we make move, the opponent will make a move to make it the 0. Yes, exactly. That's the same idea. I want to show that at the end, I want to show that if the XOR is 0, you have no choice by making it non-zero, and then your opponent will make it 0 again. And then again, you have to make it non-zero, and the opponent will make it 0 again. And you make it non-zero, and the opponent make it 0 again. So you're gonna lose this way, because at the end, your opponent is the one who makes all of the numbers 0. Exactly, we have to somehow XOR our total XOR X, but we shouldn't take away X. We should choose one of the numbers, one of the pairs that has, for example, AI's stones right now. And can you say that what should we change it to so that our XOR will be 0? I have to change AI to what, such that if XOR right now is X, the XOR will turn into 0. I have to change AI to what number, such that I will make sure that if my XOR right now is X, it will turn into 0. Exactly. I have to change one of my numbers, like AI, to AI XOR X. This way, if I change one of my numbers from AI to AI XOR X, the total XOR will be XORed with X as well. So my total XOR will be 0. So I should change one of AI's to AI XOR X, but it's not that simple. There's also one condition that we have here too. Can you say that? What is that condition? What is that condition? I know that I have to change one of the AI's to AI XOR X, but there's one condition as well. I cannot just simply choose an AI and change it to AI XOR X. I might not be able to do that. When can I do this? When can I change an AI to AI XOR X? So I know that if my XOR is X right now, I know that I want to make my XOR 0. So I should take an AI and XOR it with X. But there's a condition, exactly. AI XOR X must be less than or equal to AI. Because I cannot increase the number of stones. And because it cannot be equal, XOR is non-zero. So it cannot be equal as well. AI XOR X must be less than AI. Because I know that I can remove several stones. I should remove several stones. So I should show that AI XOR X, AI XOR X must be less than AI. So if I have some I, if there is some I, such that AI XOR S is less than AI, then I can say that I will choose that AI and I will XOR it with X. And then by doing that, it will be less than by doing that, it will be less than AI, so I can do that operation and my XOR will be 0. So I just need to prove that there exists some I such that AI XOR X is less than I. Let me move a little bit to be centered. I should prove that there's some I such that AI XOR X is less than AI. But how to prove it? Let's say that how AI XOR X will be calculated. If this is your AI, and this is your X, when AI XOR X will be less than AI? Can you say that? What is the condition? I mean, can you say that in simpler terms? When AI XOR X is less than AI? Is it really if AI is greater than X? That's not necessarily true. Assume that AI is 2 and X is 1. Assume that AI is 2, X is 1. Then AI XOR X is 3, is greater than 2. So what is the condition when AI XOR X is less than AI and when is it greater than AI? Some element greater than AI XOR X should be present. Well, that's not important. Only AI and AI X must be compared. When AI is less than X, that's not true as well, because maybe AI is 1, X is 2. AI XOR X is greater than both of them. So when AI XOR X is less than AI, I should first have some idea about when AI X is less than AI, and then I can talk if there such AI exists or not. The highest bit clash is 1 XOR X also. Exactly. So the point is that if you consider the greatest bit of X, you know, if X has several ones, if X has several ones in these positions, these are the bits that will be changed in A. So the point is that the greatest bit that will be changed in AI is the highest bit in X. And that bit must be 1 in X such that it will be turned into 0. If that bit is 1, the number, the AI XOR X will be less than AI, because AI XOR X will change that bit in A. You will see that in which bits X is 1, and you say that those bits from A will be changed. So what you're saying is that if the greatest bit of X is 1 in A, that will be changed to 0, so AI XOR X will be less than AI. If it is 0 in AI, when it will be XORed with X, that highest bit will be turned into 1. So it will be bigger. So basically what we're saying is that the highest bit in X must be 1 in AI. That's what we should show. Is it clear? So I'm saying that AI XOR X is less than AI if AI, the highest bit in X in AI is 1. Do you agree with this? If it's clear, please put a plus, otherwise put a minus. So the highest bit in X is the highest bit that will be changed in AI. The highest bit in X is the highest bit that will be changed in AI. So we can say that if AI is 1 in that bit, it will be smaller, otherwise it will be bigger. Let's talk about an example as well. For example, in case that I was talking about 2 and 1, 2 is 1 0, 1 is 0 1. So you can see that the highest bit in 1 is this bit, but this is 0 in 2. This is the first bit that changes in 2, so it makes 2 bigger. But if we had 1 and 3, the highest bit in 1 is this one, so the first bit, the highest bit that it will change in AI is this. So because in here it's 1, it will turn into 1 0, so it will be less than that. So when you just consider the first bit that X changes, for example, if X is this and your AI is, for example, like is bigger and it's just like this, the point is that if you see the first, the biggest, the highest bits in X, if it changes it to 0, it's not even important how it changed the rest of it, because this one is the more significant bit and the rest of them are not important. So you can just consider this one and you can say that if it makes it 0, then the number will be less than what it was. So basically I can say this: if the highest bit in X is 0 in AI, the number will be bigger, AI XOR X will be bigger than AI, otherwise it will be less than AI. So now I just need to show that the highest, I should show that the highest bit in X is 1 in at least one of AIs. I should show that the highest bit in X, at least in one of AIs, is 1. I know that it's getting a bit complicated, but I hope that you're following up. If at any point you were not following up, or if it's not clear for you, let me know. So I'm saying that if you consider the biggest bit on X, there is at least one number that this biggest X bit on X is 1 in that. And then I can choose that one, XOR it with X, it becomes less than that. And I make my whole XOR 0. Then I proved that I can always make my XOR 0. So now all I need to do is to prove that there is one AI such that the biggest bit in X is 1 in that AI. why is that true? Why such an X exists? Such an AI exists? Do any of you have any ideas? I haven't discussed the contest problems. Because I'm talking about Grundy numbers. That's the main point of today. Contest. I hope that we can get to solve some of the latest problems of the contest as well. I mean, I plan to solve the last 4 problems. But the first priority is talking about the Grundy numbers. So now what you need to show is that there exists some AI that has the biggest bit in X. Why? Do not forget that X is the XOR of all the numbers. Okay, X is the XOR of all the numbers, all the AIs, right? So what can I say? I basically can say that if in my XOR this bit is 1, it means that it is 1 in odd number of numbers, right? I know that X is the XOR of all the AIs. X is the XOR of all the AIs. So if this bit is 1 in X, it means that it's 1 in odd number of numbers. So basically we can say that because it's 1 in odd number of numbers, we can basically say that there is at least one of them that is 1 in this bit. Okay, so I'm saying that if you consider the first one in X, any one in X, it means that there are odd number of ones in the numbers A1 to AN in that bit. So what does that mean? It means that there's at least one AI such that it's 1 in that bit. I can just consider that one, XOR it with X, and then I make it smaller. Just let me know if that's clear or not, or do you need me to explain it again? It's completely okay if you need me to explain it again. So what I said, I just proved that there exists some AI such that the biggest bit in X is 1 in that AI, because I said that when this is 1 in here, it means that odd number of AIs have 1 in there, so it cannot be 0. And then I can XOR that one with X, so I make it smaller. So by making it smaller, I can make the total XOR 0. So from a state that XOR is not 0, I can always go to a state that XOR is 0. Therefore, I can say that I can always make the XOR 0 if it's not 0. If you had any questions, let me know. Ask me if you had any questions. Nice. Okay, if there are no questions, so then I say that I showed that if XOR is non-zero, I can always make it 0. I can make it 0. If the XOR is 0, I must make it non-zero. So the point is that assume that the XOR is not 0 at the beginning. I want to prove that I will win. I want to prove that if you play a game and the XOR of AIs is not 0, yes, definitely. I will also explain with a simple example. I will explain with the example that we had. I want to show that if XOR is non-zero, I will win the game. How? I say that first I make the XOR 0, and then you have to make it non-zero. Then I again make it 0. So XOR is non-zero. I first make the XOR 0. Then you have to make it non-zero. You have to. Then again I can make it 0. Then you have to make it non-zero. Again I make it 0. Again you have to make it non-zero. Again I make it 0. So each time I'm making it 0, you're making it non-zero. I'm making it 0, you're making it non-zero. So at the end, when does the game end? When all of them are 0. When all of them are 0, who has made all of them 0? You or I? When all of them are 0, who has made all of them 0? You have made them all 0, or have I made them all 0? I'm the one who makes it 0. at the end. I'm the one who makes it 0 at the end. I'm the one who knocks, as you said. I'm the one who makes it 0 at the end. Because each time you're making the XOR non-zero, I'm making the XOR 0. So always after your move, the XOR is non-zero. So definitely all of them are not 0 after your move. After my move, it's possible that all of them are 0. So if all of them are 0, it means that the XOR is 0. So it means that I made them 0. Okay. So my strategy is simply this. I each time make the XOR 0, you make it non-zero. I make it 0, you make it non-zero. I make it 0, you make it non-zero. And at the end, because all of them will be 0, I'm the one who made it 0. I'm the one who knocks. So I will win. So let's talk about an example here. Let's play the game on here. First, let's see that what is the XOR here. Let's write the numbers. In here, the numbers are 4, 2, let's use another color, 4, 2, 3, 4, and 3. Well, it's very simple. The XOR right now is 2. What can I do? I mean, this is very simple again. I can just remove these 2. And then whatever you do, I can copy it in somewhere else. For example, if you remove these 3, I can remove these 3. You can see that each time after my move, XOR will be 0. After your move, XOR will be non-zero. Again, if you removed 1 from it, I can remove 1 from it, and so on. Let's make this example a bit harder by changing it to 5. So I showed you that I will definitely win in here. I can remove the 2 and the rest of it is easy to win. Let's make it a bit more challenging. I want to show that even in the more challenging cases I can win if XOR is non-zero. Let's make it 5. Let's see that what is XOR is. If it is 5, it's 5 XOR 4 XOR 2. I think it's gonna be 3. The XOR. It's 5 XOR 4 XOR XOR 4 XOR 2. Yeah. XOR 2, XOR 3, XOR 3. The XOR will be 3 at the end. So there are odd number of ones here, odd number of ones here, even number of ones here. So XOR is 3. I can show that I can win the game. Why? I proved that I can make the XOR 0. How can I make the XOR 0 right now? Right now the XOR is 3. You tell me that how can I make it 0? What should be my first move? The XOR right now is 3. I want to make the XOR 0. What should I do? In this example. Any suggestion? So the XOR right now is 3. I want to make it 0. How can I do this? Take 2 stones from what? The XOR right now is 0. It is 3, sorry. The XOR right now is 3. The XOR right now is 3. I want to make the XOR 0. How can I make the XOR 0? Take 3. From which one? Tell me from which pile how many you do want to decrease. Yes. From the last one, I can make it 0 by removing these 3. And then you make a move. I made the XOR 0. Now you make a move. I want to show that I can win against you, however you win. I made the XOR 0. Now you make a move. A5. From A you want to remove 5. Or remove all from A3. That's your move. Are you sure that's the move you want to do? Okay. So your move, I show your moves with green color, my moves with red color. You remove these 3 with in your move. And then I again calculate what's the XOR. The XOR again must be 3. So you made the XOR 3 again. I have to make the XOR 0 again. How can I make the XOR 0? Can you help me? How can I make the XOR 0 again? I know that XOR is 1, 1. So I should find an AI such that AI is 1 in this bit. I should find such an AI that AI is 1, has 1 in this bit. Exactly. Remove 1 from 2. If I remove 1 from 2, it will be turned into 1. So 2 XOR 3 is 1. So if I change 2 to 1, I can see that my XOR will be 0 again. It will be 5 XOR 1 XOR 4. You can see that that's 0. So I make the XOR 0 again. So I made XOR 0 again. So what's your next move? Just suggest a move. That's my move. I removed 1 from A2. Because I wanted to make the XOR 0. I had 2 stones there. I changed it to 1. It's like I XORed 2 with 3. 2 XOR 3 is 1. So by changing it to 1, it's like I XORed the whole XOR with 3. So I made it 0. Your step is to remove all from A1. Okay, so you just want to delete all from A1. Whatever you do, I can win. So you're making XOR 5. Now I want to make the XOR 0 again. So I should choose one of these and XOR it with 5. What should I do? Can you help me? What should I do? I want to again choose one. 5 in mod 2 is 1, 0, 1. So I should choose one of them such that it has 1 in this bit. Which of them has? Which of these piles? Which of these numbers? Between 1 and 4. My remaining numbers are 1 and 4. Which one of them has this bit on? And how many will remain if I XOR it with 5? No, I proved that always I can make the XOR 0. Yes, you can remove an arbitrary amount of things. Yes, you can remove an arbitrary amount of things. Yeah. Sure. So, how many should I remove from which one to make the XOR 0 again? Can you help me with that? Sure thing. So how many should I remove from which one to make the XOR 0 again? Right now XOR is 5, right? XOR right now is 5. I want to make it 0 again. So I should find a pile such that it's 1 in this bit. Remove 3 from A4. Exactly. I should choose this 4, XOR it with 5. 4 XOR 5 is 1. So 1 should remain. So I will delete 3 from this 4. And then the XOR is 0 again. XOR is 0 again. So now what is your move? It's easy to say that now I'm the winner. It's very obvious that now I'm the winner. Whichever you choose, I will choose the other one. So for example, if you choose this one, I will choose this one. And I win the game. You cannot make a move. So I showed you that if the XOR is non-zero, I have a strategy to win. And then you cannot do anything. Is it clear? Is it clear that I'm the one who knocks the door? I hope that you're familiar with this dialogue. So say my name if it's clear. What if we generalize this game, but you can only remove a maximum of 5 balls, for example? That's a great question. That's something that we will discuss. That's a great question. So we can generalize this problem and, for example, yeah, say that as well. Yeah, we can see that how does that work. That's also a good question. That's a good problem to think about. So is it clear so far? If you have any questions so far, just let me know. Otherwise, we talk about the next thing. So this is called the Nim game. This is a very famous game. Let me also share with you the Wikipedia page of Nim game. This is the link. You can read about it in here as well. So you can read about it in this Wikipedia page as well. And it tells you that how does the game work. It's like it says that we have several heaps, and for example Bob takes 2 from A, so it returns to 1, then Alice takes 3 from C, then Bob takes 1 from B, and at the end Bob takes entire C heap and win. So it tells you that how the game is, and it then talks to you about winning positions, and it just talks to you about the mathematical theory. And in here it will talk about XOR, and it tells you that if XOR is 0, the second player will win, otherwise the first player will win. Also, there's a good resource in Uselful guide, I think. Let me find that for you as well. I put all of the links in the descriptions of this video as well, so that they won't get lost. Let me send to you the link of this Uselful guide page. This is also a very good resource, this Uselful guide. And even more generalized situation. There is a game represented by DAG, and multiple instances of this game happen parallel, and you can choose to make a move in any of the games. Yes, that's also possible. We can talk about that as well. Yeah. Why Alice, Bob rich everywhere? Yeah, Alice and Bob are very famous. I mean, because instead of A and B, they use Alice and Bob, and it's also, as I know the backstory, it also promotes gender equality. One of them is girl, one of them is a boy. So it's very, you can see it everywhere, especially in game theory, because it's about 2 people playing a game. Usually the names of Alice and Bob will be used. Hey Sharon, are you vegan? I'm not. Why? More examples? Yeah, we will talk more now, next. But we do not play this game again, but yeah, we will talk more about the next things. What could you think with the frequency of game theory questions in Div 2? Well, it's once in a while. It's like, well, it's not as common as DP, definitely. But it's one of the, I mean, it can be as common as probably greedy. You can just see that. I mean, if you want to just have some estimations, you can go to problem set of Codeforces. This is just good for some estimation, because the tags are not always accurate, and sometimes it has other solutions as well. You can, for example, search for games and see that how many pages are for games. There are 3 pages for games. So these are the problems which are tagged with games. For example, if you just apply dynamic programming, it definitely is more. DP is definitely more. DP is 23 pages, so it's a lot more. But for example, if you have like something else, for example, like, I don't know, like geometry or hashing or some, DP is the most famous one. For example, let's choose hashing. Hashing is also 3 pages. Or let's see how many greedy is. Probably greedy is more. Let's see how many greedy is. Greedy is a lot, sorry. Greedy is 31. Yeah, it can, because greedy is not necessarily the main object of the solution. You can also apply greedy somewhere as well. But yes, you can, if you want to have some approximation, you can do this. For example, ternary search again must be around the same. Yeah, it's just 1 page. So that gives you some estimation. Egypt's IOI names are funnier, especially Cleopatra. I didn't know that. How well does Codeforces help chances of making IUI? It does. I mean, Codeforces is important, definitely. It makes you a better coder. Although after some points, you have to also solve hard problems, not only problems in 2 hours, but you have to solve more harder problems, spending more time. But still, Codeforces is very important always. You're welcome. We're not done yet though. I'm gonna talk more. Cause was there many game theory questions? Yeah, I told you that there are many game theory pattern-based problems, etc. And also in theory, in algorithms is important as well. I just told you that I also had 3 papers, 2 of them are about game theory. These 2 are about game theory. Okay. Also, how did you leap from Codeforces trash to Codeforces God? Do you mean about going from newbie to IGM or something else? Let me get back to here as well. If you mean how did I get to IGM from newbie, it was basically training and solving a lot of problems. It's not very hard or special answer. Yeah, it's basically about solving a lot of problems. Yeah, I've talked about it a lot before, about what did I do in the different periods in my topic streams. I should make a video about that. Yeah, my research papers, yeah, 2 of them. The papers that we wrote are about game theory. Yes, game theory is a very important field that is very useful. Also in economics, in many different fields, they are very important. There are also some other aspects, beautiful aspects of it, like prisoner's dilemma and some things like that. These are also very important. That I believe I should talk about them as well sometime. If you want, I can explain my papers as well. For example, well, the papers is about increasing. I mean, in Codeforces, you're solving a problem that someone has designed, the solution is known, everything is known. But when you research and you write a paper, you want to solve a problem that is not solved yet. A problem that's, for example, one of the papers that we had, we proved something, we just improved something from d squared to d log d in this paper that was published in 2022. So that's also something that game theory in that is very something that is many people are working on it, and it's very active field. Also in Codeforces, as you have seen, there are so many problems as well. I'm in computer science. Okay, so let's talk about the next thing. About the research papers, you can find it in Google Scholars. Yes, most of them are impartial. Yeah. So let's talk about the next thing. We're not done yet, as I said. Let's talk about the next thing. Well, this introduces us to something more important. Well, I want to use this idea of this intuition of Nim games to something, to solve this problem, to solve more problems. I want to generalize this Nim problem to be able to solve problems like this. What do I want? I want to first change the Nim game a little bit. Assume that in the Nim game, not only we can decrease the numbers, but we can also increase them. I mean, we have these piles of stones, A1, A2 to AN. Again, we have A1, A2 to AN. These are the piles of stones that we have. And each player not only can choose one of the piles and decrease it by a positive integer, but they can also choose one and increase it, but they can only do it 3 times. So there are 2 players who playing. Again, each one of them can choose one of the piles and decrease them, or at most 3 times they can increase them. So now who will win the game? If both of the players have the chance to increase the number of stones in a pile, but only 3 times. So it's like each one of them have 3 tickets, and they can use one of their tickets and increase the number of one of the piles. Can you say that's who will win the game? About your questions about the way of studying and solving problems, I can talk about it at the end of the stream. For now, maybe it's better if we focus on talking about this, about our topics. But I will talk about it at the end. Okay, so what do you think? It doesn't matter because you can decrease whenever they increase. Exactly, that's correct. That's correct. Well, basically, again, it doesn't matter. It doesn't change anything. If I'm a winner right now, after adding this, I can still win. It doesn't change the game because I can assume that you cannot increase and just do my strategy with XOR. I can do my normal Nim strategy and assume that you cannot increase. Only when you increase, I can undo your action by decreasing it back again. For example, if you increase something by 10, I will, in the next turn, I will decrease it by 10. It's like you didn't do anything. It's like I undo that. And this way I can still win the game. So it doesn't matter if you can increase it 3 times or increase it any limited number of times. Why I set some limits? Because I want to make sure that the game will end at some point. So it's okay if you want to increase as well, because even if you increase, you will change the XOR. And I can make it 0 again afterwards. So if I just show that the game ends, even if you increase the number of stones in a pile, that doesn't change anything. And I'm still the winner. Do you agree with that? So, do you agree with this? If, basically what I'm saying, it doesn't matter. If you agree with this, put a plus or use the emoji again. I'm saying that even if you can increase the number of stones in a pile, I don't care about that. I can still win the game. And whenever you just increase the number of stones in a pile, I will decrease it back again. That's what I'm saying. I know that now maybe, I mean, as the stream goes forward, there will be more lag in the stream. So, okay, if you had any questions at any point, let me know. If you wanted me to explain anything again, let me know to explain that again. So it's also okay if you can increase it. So basically, the Nim game just needs to be like this. From a pile with X stones, you should be able to change it to all the stones less than that, all the numbers less than that, all the number of stones less than that. So all of the numbers from x minus 1 to 0, you must be able to change it to them. And about x, you should not be able to change it to x. I mean, from x you cannot go to x. You cannot choose a pile that has x and after your move still set it x. You cannot set it equal to the same value. So you should be able to set it to any number less than that. You should not be able to set it to the equal value. And about the numbers greater than that, it doesn't matter. You can do that or you cannot do that. And also you need to show that the game is finite. So the more general form of the Nim game is that you just show that the game is finite, and for each x you can set it to any number less than that and not to the same value. And about the greater values, it doesn't matter. What is the duration of this stream? It's at least 2 hours, but maybe today it takes a bit more. Today probably it gets a bit more because I want to talk more about this stuff to reach to a good point. But probably 2 hours and 15 minutes or something. Yeah. Right now it's been 130 minutes, as you can see below the video. Okay, so that's the more general form of Nim game. You should be able to set it to any smaller number, not the same number, and the greater numbers do not matter, and the game must be finite. Now, can I set some numbers here for the different vertices? Set numbers such that from each number, I can go to the numbers less than them. And I cannot go to the same number, and the numbers greater than them do not matter. Is that possible? So is it possible if I can choose numbers for these vertices so that from each vertex I can go to vertices with numbers less than them? I cannot go to the same number, and the numbers greater than them do not matter. I probably can, probably can't. I don't care. How should I set the numbers? For example, what should the number of this last vertex be? I mean, if I want to make it similar to a Nim game, having a piece in here is like having a pile with how many stones? Do you agree that, I mean, what do you think? What should be the number of this vertex, this last vertex? If I wanna give you some intuition, I will ask you this. If I wanna make it resemble Nim game, the Nim game, how many, it's like how many stones do we have in a pile? Exactly 0. So we start with 0 for this one. And how do you think I should define the numbers of the rest? How do you think I can use the idea so that from each vertex I can go to all the numbers less than that, not the same number, but the numbers greater than that do not matter? For example, what should the number of this vertex then? If I want to go to all the vertex less than that, not to the same number, numbers greater than that do not matter. What should be the, oh sorry, again I'm making a mistake. I first should ask this, sorry. What is the number of this one? What is the number that I can give to this state? What is the number that I should give to this state? I want to be able to change it any number less than my number, not the same number, and the numbers greater, the greater numbers do not matter. It can be 1, exactly. That's a very good guess. Exactly. It's not a guess though, it's right. I mean, because it has an edge to a 0, it can be 1. What about this one? What can this number be? I guess we have some lag and it's taking some time. Yes, 2. Exactly. Because it has an edge to 0 and 1. Awesome. Now what about this one? What number can I assign to this one? 0. And what about this one? Three, exactly. So do you see the pattern? It's like we are setting each number to be the first number that is not in its outgoing edges, right? It's like we set each number to be the first number that is not in the outgoing edges of that state. Do you know that what is it called, the first number that is not contained in a set? It's like if you have a set of numbers, we are looking for the first number, the smallest number that is not in that set. For example, in here the outgoing edge is 0. The first number that is not is 1. The outgoing of this one are 0 and 1. The first number that is not is 2. The outgoing of these ones are 1 and 2. The first number that is not is 0. For this one, the outgoing edges are 0, 1 and 2. The first one that is not is 3. Exactly. It's called MEX. Minimum exclusive number. X, I think X means X. So let's see. So it's like the mix of the number. Maximum excluded value. So probably you think like it should be MEV, but it's MEX. X stands for X. MEX is minimum excluded value. So yes. So the point is that each time we're setting each number at the mix of its outgoing edges. So for example, this one, what is the value of this one? The one here. What the value of this one should be? 1, exactly, it should be 1. Because 1 is the first number that is not in its outgoing edges. What about this one? What should this one be? Yes, it's okay. This one points to a 3, but I told you that the numbers greater than that do not matter at all. It's okay if one has an edge to 3. It's okay. I told you that. It's okay if you can increase the number of files as long as you show that the game is infinite. The game is finite. Sorry, it's not infinite. The game is finite. And you can change it to every number smaller than your number. And the numbers greater than do not matter. Maybe you can change to some, you cannot change to some. I do not matter. I don't use it. The winner does not lose it. And even if the loser does that, use that, it's not going to be helpful for him. Because the winner can undo their move. So it's okay that one has an edge to 3. So yes, this one is 0. And what about this one, the first one? Yes, exactly. XOR can be forced regardless. Exactly. This is not 4. This cannot be 4 because it does not have an edge to 2 and 1. You need to have edge to all the numbers less than yourself. The numbers greater than yourself do not matter. Maybe you have edges to them, maybe you do not have edges to them. You just need to guarantee that you can go to any number less than that because the winner needs to ensure that. And you cannot make it to the same number because it's still the winner needs that. In order to make the XOR 0, we need that, and we need to not be able to change a number to itself to make sure that the loser has to change something and makes the XOR non-zero. And yet this one is 2, as you said, exactly. So these are the numbers. So what I'm saying, it's like, if you take a look at this game, first of all, I told you that if there are 2 stones on the same place, we can remove them and it doesn't change the game. Even in XOR, they will be deleted automatically as well. And the point is that I'm saying that you can look at each of these pieces as a pile in our Nim game. It's like, we have a pile here with 2 stones. Let's use another color that is more clear. It's like we have a pile of stones with 2 stones here, a pile of stones with 0 stones here, a pile of stones with 3 stones here, and a pile of stones with 1 stone here. With 1 stone here. Who will win the game here? Who's the winner? If this was a Nim game and we had these 4 piles of stones, who was winning the game? The first player or the second player? The numbers are 2, 0, 3, 1. Who will win the game? Second player, exactly, because the XOR is 0. The XOR in here became 0. So the second player will win the game. And I show you that in this game, it's exactly like Nim. Why? Because each time you can subtract each pile by any number that you want. For example, you can change this 3 and move it to 2, or move it to 1, or move it to 0. It's like you're subtracting those many piles, those many stones from that pile. It's also possible that sometimes you increase some number. Probably, for example, you move this 3 to this 0 to this 3. By doing that, it's like you're increasing it by 3. But as long as you can ensure that the game is finite, and here the game is finite because you're on deck, it's okay. When he moved it to 3, you can move it back again to 0. So it's okay. You can undo that. It doesn't matter. Anyway, he makes XOR non-zero. So the point is that if the XOR at the beginning is 0, you have to make it non-zero because you have to change something. You have to move one of the pieces and its value will change. So XOR will be non-zero afterwards. If the XOR is non-zero, you always can choose one of them and subtract some value from it. And because you ensure that all the smaller numbers are there, you can subtract them to make the XOR 0 again. And at the end, you know that all of them must be at the end. All of them must be 0 at the end. So who's gonna make all of them 0? The one who makes the XOR 0. So that one is gonna win the game. So this is how you can prove that if you choose the numbers like this, if you start from the end, you put 0 on the things, and make each number the max of its outgoing edges. Make each number the max of its outgoing edges. At the end, you just need to XOR the values on these different stones. It's like we have several parallel games. For each parallel game, you are defining, each parallel game will be mapped to a pile of stones. And then at the end, you will XOR the number of stones in each pile, then the number that you assign to each of these parallel games. In here, it's like we have 4 parallel games. We have 4 different pieces. And I showed that these 4 parallel games can be mapped to 4 piles of stones. Those 4 piles of stones were parallel as well. You could choose any one of them and remove as many as you want. So basically, you just need to see that what are the numbers of these parallel games and XOR them. If the XOR was 0, the second player will win. Otherwise, the first player will win. And that's all about this game. And that's all about how to calculate who will win the game. Is it clear or not? The undoing move is cold. Yeah. Is it clear? If it is clear, please put a plus or use the emoji. Okay, nice, awesome. Awesome. Sorry, I don't know why messages were brought up. Sorry. So, yeah. Awesome. So the main point was that we assigned some numbers and we showed that it's like we have those many number of piles. And these numbers are very famous numbers. How are these lectures are scheduled? Generally, these lectures are designed to be scheduled on Fridays. So from now on, I'm trying to make sure that they will be held on Fridays. From the next Friday, probably. And anyway, I will tell you the schedule of lectures in the Telegram channel, and I will set them in Codeforces streams as well. You can join I invite all of you to join the Telegram channel to stay alert of the streams. Anyway, these numbers that we defined are very famous numbers. And they have a very famous name. And you can guess that what is their name right now. What do you think the name is? These are the very famous numbers which are called Grundy numbers. Exactly. Grundy numbers are exactly this, what I told you. These are called Grundy numbers. It's like for each state, the Grundy number of that state is the max of the Grundy number of its outgoing edges, its outgoing states. That's all. So these are just names, and we showed that we proved everything from the beginning. We saw the reasoning behind everything. I really encourage you, if you did not completely understand it, watch the recording of those parts again, those parts that you think that you need to listen to again, because it's very important that you completely find the intuition behind everything and understand it completely. It's not hard. I could understand it completely, so you can understand it completely as well. Sure, again, and try to comprehend exactly how was all the proofs, everything. How did we prove it for the Nim, and how did we apply the same intuition of Nim here, and how XOR can be forced here as well. In here again, each time I can make the XOR of these numbers 0, and my opponent has to make it non-zero. Again, I make it 0, the opponent makes it non-zero. I make it 0, the opponent makes it non-zero, and goes on. And with this, with doing this automatically, if there are two stones on the same place, because the XOR of these two, the values of the Grundy of these two are the same, they will be XORed and they will be deleted. So even if you have two at the same point, sorry, the tablet was not shared. If you have two at the same point, they will be extract and deleted. How do you come up with an elegant solution which is easily understood, generally made? Because learning this is so much easier than inventing this. Yeah. Well, you have to, in order to come up with the solutions, you need to solve a lot of problems, as I told you. You have to solve a lot of problems around your current rating. I personally have solved like 3,000 problems from Codeforces. So you have to solve a lot of problems to get more familiar from it. And I'm really happy if you easily understood these things. I really am happy about that, if it helped you to understand this well. But if you want to come up with a solution, it's completely okay. At the beginning, it takes time. You cannot expect to just become a grandmaster, for example, in 2 months of a starting CP. So you have to be patient and solve problems, spend a lot of time. You have to spend maybe more than 7-8 hours per day, I believe. Do you know any resources for more advanced covers in impartial games beyond Nim and Grundy Numbers? Yeah, most of them can be modeled to these. I think that if you want to solve problems from Codeforces, there are several hard problems on Codeforces as well that you can solve. But you can, more than that, if you want to search for some other resources, I recommend to you to search, because I don't know many resources about that. But as I told you, I'm thinking about making a course for these things as well. When you believe that you have no ideas anymore, when you believe that you're stuck, I said it many times in the topic streams and live streams before. When you feel like, continue thinking as long as you're not stuck. You can also watch my interviews with big competitive programmers like Omnik, Reina, Ors, Adamant. I have interviews with these people, and we talked about this with them as well, or Ali Reza Kavihani. And you can see that's what they said as well. For example, you can easily see the interviews here. Interview with CP Legends. I had interviews with 5 people, and you can see that. How do they say about it as well. I really recommend watching these as well. Especially the interview with Omnik, I really liked it. An interview with Arash, they were really interesting. The rest of them were very interesting too. But Omnik said very many sentences that could raise up arguments. For example, he said that anyone can become a grandmaster or anything, and there are so many different ideas on different things that he said, and it was a very interesting interview in Omrik. And also Arash is interesting as well, because he started IOI and he had IOI, and right now he continued growing, and right now he has even more than 500k, more than 700 or 800k right now per year. And that's also interesting, and he talks about all this. 25 is too late to start Codeforces? Not necessarily. It depends on what you want. If you want to have job interviews, competitive programming helps you. You can solve lead code problems. I'm gonna observe lead code contests as well in this session, in this channel. And I think that if you want to get a job in a company, in interviews, most of them competitive programming is arduous. Sure. No, I hope that it helps. And guys, I wanted to tell you something as well, in case you want to support my work, because I'm spending a lot of time and I'm thinking of advancing everything, bringing up everything to the next level as well. This is not mandatory as well. I do not expect anyone to do this, but if you want, you can support my work here in this link that I've shared with you in the descriptions below. I've just added this, and as I said, you don't have to do anything, but if you do this, it makes my work simpler to continue doing what I'm doing. So in case it's really helping you and you want to support me to do it more often, be able to do it, you can support me from here. And also, if you are looking for a personal tutor, you can do that in the link that you have in here. I made a website for that as well. You don't need to email me anymore. If you want, you can just come to this website. Okay. Sure thing. So let's continue. We're not still done. Let's see that how many minutes have been passed. It's like around 2 hours right now. So let's continue talking about this. You asked a question. You said that what's the case if we can each time delete at most, for example, 5 stones from each of them. What happens if you can delete at most 5 from each pile? Let's say that we have 1 pile. Let's see that what the Grundy numbers are gonna be if we have only 1 pile. And these are the number of stones that we have in this pile. 0, 1, 2, 3. I want to find the Grundy numbers for each one of them. We know that we can delete at most 5 stones from each pile. So we change the problem. Instead of saying that you can delete as many as you want as long as it's positive, you can delete up to 5 stones. You can remove up to 5 stones from each pile. Then what is the Grundy number of 0? What the Grundy number of 0 is? So I want to find the Grundy number of each number. I want to find the pattern. I want to find out that what is the Grundy number of each of the numbers. So what's the Grundy number of 0? Yeah, Grundy number is exactly what I said just now. I said that those numbers that we defined here are called Grundy numbers. These numbers that we defined here are very famous numbers that we call them Grundy numbers. So, exactly, mix of an empty set is 0. So it's gonna be 0. Exactly. So this is gonna be 0. What is the Grundy number of 1? If we have 1. So let's go a bit faster. What is 1? 1, exactly. What is 2? 2. What is 3? Yes, that's a good guess. Yeah, exactly. Same as number till 5. Exactly. 3, 4, 5. Because we can see that, for example, why is this one 5, 4? Because it has an edge to 3, to 2, to 1, and to 0. So it's gonna be 4. 5 is 5. What about 6? 6 is where it gets interesting. What is the Grundy number of 6? If we start with 6, what is gonna be the Grundy number of that? Exactly, it's 0 because all its edges are to 1 to 5. So it's 0. What about 7? What do you think is 7? Exactly, 1, because it has an edge to everything other than 1. Again, 8 is 2, 9 is 3, 10 is 4, and so on. So you can say that each I, the Grundy number of each I is going to be I modulo 6. And that's all. The Grundy number of each pile is going to be I modulo 6. So if you have several piles, you see that what is the Grundy number of each one of them. You have several parallel games. And you XOR the Grundy numbers of them. And then when you XOR the Grundy numbers of them, if it is 0, the second player wins, otherwise the first player wins. In the normal Nim, because you have edge to everything before yourself, Grundy number of I is really I. So if we want to reapply, Grundy numbers are designed and made from the Nim game. But if we want to reapply the Grundy numbers to the Nim game, because it's like everything has edge to everything before that, each I, Grundy number of each I is going to be I. But in here, because each number has an edge to the last 5, you can see that there's a pattern. Every 6 numbers, it repeats 0, 1, 2, 3, 5. Again 0, 1, 2, 3, 5. 0, 1, 2, 3, 5. And so on. So you will calculate the Grundy number of each one of them and you XOR them at the end. Is it clear? If it is clear, again, please put a plus or use this emoji. And all of that I said is not enough unless I also solve a problem from Codeforces from them. So using these topics that we said, I want to also solve a problem from Codeforces. So let's bring this problem now that you're all okay with that. Let's talk about this problem, 87C. This is a very famous problem on Codeforces that uses Grundy numbers. But it says that 2 best friends, Seroja and Gena, play a game. Is Tourist the author of this? Gena? I think it's short for Gennady. Anyway. Initially, there is one pile consisting of n stones on the table. During one move, one pile should be taken and divided into an arbitrary number of piles consisting of a1 greater than a2 greater than 2ak stones. And the piles must meet the condition a1 minus a2 is equal to a2 minus a3 equal to 2ak minus 1 minus ak equal to 1. What does it say? It says that you have several piles of stones. Each time you can choose one pile of stones and change it to several piles such that these piles, the number of stones in each pile is one more than the previous ones. The numbers are consecutive and their sum is equal to the value of this pile. So you want to just change this pile. For example, assume that you have a pile of 5 stones. You can change it to 2 and 3. You can remove this pile of 5 stones and make one with 2 and then one with 3. And then you can change that 3 to 1 and 2. Or you can change 9 to 2 and 3 and 4. So you can just change, if you have a pile with, for example, x stones, you can change it to some piles with y plus 1, y plus 2, and so on, to y plus k, such that the sum of these numbers, the sum of these y plus i's, is equal to x. So their sum must be the same, only you just make a pile into different piles. The player who cannot make a move will lose the game. You have to say that if both players play optimally, and this k must definitely be greater than 1. Okay, this k must be greater than 1. Y must be at least 0, because I start from y plus 1. Y plus 1 must be positive, so y must be at least 0. And k must be at least 2. The player who cannot make a move will lose the game. You have to say that if both players play optimally, who will win the game. For example, if we start from 5, we can change it to 2 and 3. And then we can change this 3 to 1 and 2. And then we have 2 and 1 and 2, and we cannot make any more move. So the first player will lose then. So I hope that the problem is clear. If it is, if you have any questions about the statement, let me know. Otherwise, we start talking about its solution. Russian names, yeah, these are Russian names. So Grundy number will be mix of the XOR of the Grundy number of the resulting stacks, right? Exactly. The Grundy number will be mix of the XOR of the Grundy number of the resulting stacks. Exactly. Grundy number of 1 is 0, and then somehow make range query XOR. Good ideas. So now we want to make Grundy numbers for each number. So g of I is supposed to be Grundy number of I. Let me get back to tablets. G of I is the Grundy number for I. For example, as you said, g of 1 is 0. G of 2 is 0 as well, because we cannot do anything. What is g of 3? Let's just write it for several numbers. What is g of 3? Grundy number of 1 and 2 are 0, yeah, because we cannot make a move. Yes, Grundy number of 3 is 1. These have no edges to any other state, so they are 0. But 3 has an edge to the state of having 1 and 2. And if we have 1 and 2, it's like we have two parallel games. XOR of each one of them is 0. The XOR of this state is XOR 0, which is 0. So if we can go to 0. I mean, do not forget that we do not have an edge to this and an edge to this. We have one edge to 1 and 2. We have one edge to 1 and 2. And because the XOR of each one of them is 0, the XOR of that game will be 0 XOR 0, which is 0. And then we can say that, therefore, we have an edge to 0, so g of 3 is going to be 1. What is g of 4? Yeah, time to get hand dirty. No, I just want to get some clue. I want you to completely understand that how the XORs are calculated. See how we go to a game that it has several parallel games. So in order to see that what is the Grundy number of that states, we have to XOR the Grundy number of those parallel games, and then we have edges to those states. We have an edge, for example, from 3 to the state of having a 1 and a 2. The XOR of that game is 0. From 4, we have an edge to nothing. What about from 5? What is g of 5? What do you think g of 5 is? One suggestion is 2. Any other suggestions for g of 5? Thank you very much, Dr. Deville. Zero, 2, 2. So we have two suggestions, 0 and 2. So see that which one is correct. 0 is correct or 2 is correct. Well, do not forget that 5 does not have an edge to 2 and an edge to 3. 5 has an edge to 2 and 3. So the state of 2 and 3, you know? So from the state of having 5, we can go to the state of having a 2 and a 3. We have to see that what is that state, right? We have to see that what is the Grundy number of that state of having 2 and 3. What is the Grundy number of this state? We know that the Grundy number of 2 is 0. The Grundy number of 3 is 1. So what is the Grundy number of these states? What's the Grundy number of this state? Grundy number 4 is 0 because you cannot change it to anything. You cannot go to any states. It doesn't point to anything, exactly. It doesn't point to anything. Exactly. But 5 has an edge to the state of 2 and 3. So you can go to that state. What is the Grundy number of that state of having a 2 and a 3? Well, the point is that it's like you have again two parallel games. One of them, Grundy of one of them is 0, Grundy of one of them is 3. So the Grundy number of the final thing is 1. So it's like 5 only has an edge to a 1. You know, it's not like it was 2 if we could change 5 to 2, or we could change 5 to 3. So it was true if we could change 5 to 2, or we could change 5 to 3. But when right now we can change 5 to 2 and 3. So we remove 5 and we do not choose to either add 2 instead or choose 3 instead. We remove 5 and choose 2 and 3. So it means that both of them will be added. So that state, the XOR of that state is 1. So 5 only has an edge to 1. So it's going to be 0. G of 5 is 0. Okay. Every number is not necessarily 0 because we do not need to break it into 2 consecutive numbers. We can break it to more numbers. So it's not necessarily 0. For example, for 10, you can break it to 1 and 2 and 3 and 4. Which doesn't give us a good answer because the Grundy of that state is going to be, the Grundy of that state is going to be 0. It's going to be 1. So the Grundy of 10 is going to be 0. Yes. So, yeah, that's not a bad idea. That's not a bad idea. So, let's continue. So, this is how the Grundy numbers of our states can be calculated. For example, g of 6 will be again be equal to 0 and so on. So, we just need to find out for each one of them to which states we can go. The point is that we can look forward. Instead of looking backward, we can look forward. Let me show you the code to better understand that's how we want to do it. Let's see, where was it? Okay, here. So let me show you the code. Well, if you take a look at it, I first say that you have 0 and 1 and 2 are 0. And then I start from 1 and go to n. And the point is that for each one of them, let's forget from these points. Let's forget this part for now. Let's consider this point. In this point, I'm saying that, assuming that I start from I consider that so far I know the Grundy of all the numbers from 0 to I. Okay, so far I know the Grundy numbers of everything from 0 to I. Grundy number of everything from 0 to I is declared. I know all of them. So what I do is to go backward and say that, okay, I start from I. I know that from 2i minus 1, for example, I add I minus 1 to I. I know that from the state of 2i minus 1, I can go to the state of having I and I minus 1. The Grundy of that is g of I x or g of I minus 1, right? So, first of all, in the vector of 2i minus 1, I will push back g of I x or g of I minus 1. Then I add I minus 2. My sum is gonna be 3i minus 3. In the vector of 3i minus 3, I will push back the Grundy of gi x or gi minus 1 x or gi minus 2. gi minus 1 x or gi minus 2. In coding, as you can see, XOR can be written like this. X or gi minus 1, x or gi minus 2. So I have a vector for each number that to which states I can go and what is the Grundy number of them. So I will just keep storing them. I look forward. I assume that I know everything from 0 to I, and then I go backward. I consider several consecutive numbers, and I say that. Assume that I add these numbers together. Assume that I add these numbers together to their sum. I see that to which states I can go, and to their sum I will push back to their vector the XOR of the Grundy numbers of these numbers. So basically I go like this. And when I come to something, I know it's vector already. I know that where it can go. I just store some last vector. It says that what is the last time I've seen something. I want to calculate the max of this vector. I'm looking to calculate the max of this vector. Let me see if you had any questions. Yes, I will tell again why g of 5 is 0. Yes, I will tell you that again. Let me say that again here. I'm saying that from the state of 5, you can go to the state of 2 and 3. Okay, so instead of having a 5, you're gonna have a 2 and a 3. So consider the state that you have a 2 and a 3. What is the Grundy of that state? What is the Grundy of that state that you have a 2 and you have a 3? If you have a 2 and a 3, what is your Grundy number? Grundy number of that state. Do not forget that we are calculating Grundy numbers on the states. Okay? Exactly, it's going to be G2 or G3. So these states, the Grundy number of these states, we care about the Grundy number of its states, not what is inside it. We have a game that we have a 2 and a 3 in it. Okay? This game, the Grundy of this state is 1 because it's 0x or 1. It's not like we change 5 to 2 or we change it to 3. It's not like we have 2 outgoing edges from 5. We have only 1 outgoing edge from 5 to another state. There's only 1 outgoing edge from 5. And that outgoing edge goes to the set of 2 and 3. What is the Grundy of that state? That Grundy of that state is 1. So 5, the state of having only a 5 goes to a state that has 2 numbers and its Grundy is 1. So the Grundy of these states is going to be mix of that is going to be 0 because it doesn't have an edge to any 0. And as you saw here, starting from 5, you're going to lose the game. So its Grundy cannot be 2. And if you get back to here, let me also say this to you. If you take a look at Grundy numbers, just look at the Grundy numbers and winning and losing states. Do you see any pattern in here? Do you see any similarities between win and lose and Grundy numbers? So what's the pattern that you see in here? How win and lose are related to Grundy numbers? Exactly. When it's 0, it's lose. When it's 1, it's win. Exactly. So it's like, as I said, it's like we are generalizing win and lose. As I said that different wins are different and we have to generalize win and lose. Grundy is a generalization of win and lose. And you can see that why 0 and non-zero acts like lose and win. Because we know that from a Grundy of 0, all our outgoing edges must be non-zero. And from a Grundy of non-zero, we should have an edge to at least 1 0. So it's very similar to win and lose. So 0 is exactly like lose. Its outgoing edges must be non-zero. It's like its outgoing edges must be win. A win is something that it has at least 1 edge to a 0. So it's exactly like win. It has an edge to a lose. So Grundy of 0 means a lose state is a generalization of lose states, and non-zero is a generalization of win state. It's like we have different wins. It's like we have a win at layer 1 and we have a win at layer 2 that not only has an edge to a lose state, but also it has an edge to a win at layer 1. And then we have a win at layer 3 that not only has an edge to a lose state, but it also has an edge to a win at layer 1 and also has an edge to a win at layer 2. It's like a generalization of win states. As I said, win states are different. And it's important if they have an edge to a different win, to another win or not. And these are important for us. So 5, we know that 5 is a lose state. So its Grundy is 0. And why is it 0? Because it can go to the state of having 2 and 3. And 2 and 3 is a win state. Because you can change 3 and you will win. Because its Grundy is 0x or 1. So for 5, the Grundy is 0. Is it clear now why the Grundy of 5 is 0? If it is clear now, please put a plus or use this emoji so that I can ensure that it's okay. If you have questions, also let me know that you have questions about it. Okay. Nice. Okay. So then let's get back to the code here. In here, I'm just calculating the Grundy of the states. I'm saying that if I add everything from I to j, j starts from I and goes backward. I'm assuming that I'm adding everything from j to I. I calculate the XOR of this range. This X will get updated whenever I see another J. So X is XOR of everything from J to I. S is the sum of everything from J to I. And then I say that if J was less than I, it means that I have at least two numbers. Because I start from J and go to I should have at least two numbers. In vector of S, I will push back X. It means that from S, I can go to the Grundy of X. Okay. And then, this part is not important for now, I will explain it later. In here, I want to calculate the max of this vector. How do I calculate it? I need to see that, what are the numbers that I saw in my vec of I? Each number that I see in vec of I set it last equal to I, and then I say that I start from 0, while last of g of I was equal to I increase g of I. The order of this will be at most the size of the vector, so it's going to be okay. As long as last of g I was I, it means that this number exists in outgoing edges of me, in vec of I. So I will increase g of I. At the end, I will have the Grundy of I. And at the end, I just say that if g of n was non-zero, I will see out -1, otherwise I will see out ans. And this ans is important because not only we have to say that who will win the game, we have to also output the first turn as well. We have to output that what the first turn is. If you can make the win, you have to say that you have to say print some k if you can win that represent the minimum number of piles that you can turn it into in the first step. So I said that if S1 is equal to n, it means that it's something that we can go to, and it's a loser state. At the beginning we can go to that. Its Grundy is 0. Ans will be equal to minimum of ans and I minus j plus 1. So that's all about this. Did you understand the solution to this one? Is it n squared or not? No. Well, n is up to 10 to the 5th. And it gets accepted. Why? It's not n squared because I continue as long as my sum is less than n. And the point is that when you start from I, you are summing up some distinct numbers. You can sum up at most of SQRT distinct numbers such that the sum stays less than n. Because if you have more than 2 times the roots n numbers, because they're different, at least they are from 1 to 2 times root n, and the sum of these numbers is going to be greater than n. So the point is that this 4 takes at most SQRT steps. So our total time complexity is going to be n roots n, and it's going to be okay. Yes, it's SQRT. It's SQRT. Developer role and CP with maximum efficiency. Well, I sometimes don't manage it well. As you see, it's been a while that I'm not doing good in streaming, but I'm back now. I will manage it again. Okay, so is it clear? From when I went to Iran, when I left US, I had some issues, you know, I couldn't manage things well. For example, I couldn't do the streams, etc. But previously, yes, I was really working hard to manage it. If you have any questions, let me know. Otherwise, put a plus or use this emoji. Maybe the solution is luck. This solution is not luck, but if you have another solution, happy to see you, Hardik. Thanks. Do you think LGMs can come up with entirely new algorithms during a contest? I don't know. But you know, every problem has its own algorithm in a sense. I mean, the difference between algorithms and solutions is that algorithms are the solutions that will be applied elsewhere as well. So basically yes, because probably they can come up with a solution that can be applied to many other problems as well. I mean, when you can apply a solution to many different problems, that is going to be called an algorithm. So yeah, how to master in DSA, I'm going to talk about it. So okay, now that it's okay, let me solve the last problem of contest as well today. As you know, let me show you the contest. Topic streams contest, today game theory contest. We have this contest here. You can see the contest from this link. I will talk about it, sure. I will talk about the course that I probably want to make as well, and I will talk about it at the end. So if you go back to this contest, if you take a look at the last problem, Game of Stones, well, it basically says that we have the Nim game. The only difference in this Nim game is that you cannot remove the same number of stones from a pile twice. You cannot remove the same number of stones from a pile twice. Let me send the problem from Codeforces as well. The ID of the problem is 768E. So I'm giving code chef contest and the E problems. Yeah, probably it's not good to say it here. You should have waited till the rest, till the end of the contest. But yeah, you can take a look at it after the contest, guys. I guess that the people who are in the stream are not participating in the contest, so I hope that there won't be any issues. But it's better if you wait till the end of the contest to talk about these things in general. So anyway, this is just saying that we have the Nim game. The only difference is that in this modified version, no move can be made more than once on a pile. For example, if 4 stones are removed from a pile, 4 stones cannot be removed from that pile again. And we have n piles, and you can see that for each SI, the number of stones in that pile is at most 60. The number of stones that we have in each pile is at most 60. So what can we say? We want the Grundy numbers for everything from 0 to 60. If we have those Grundy numbers of everything from 0 to 60, then we can solve the problem. It's just enough to XOR these Grundy numbers and we're done. But how can we calculate the Grundy numbers? One idea is bit mask. We can have a bit mask for a state. We can just have that how many stones are left and which moves have we made so far. We can have a bit mask that, okay, I've made the move of 1 stone, if I moved the move of 2 stones, if I made the move of 3 stones, and so on. I can have a bit mask, but this bit mask is gonna have 2 to the power of 60 ways, which is too large. But here we're gonna use a very intelligent idea. We're gonna use a very intelligent idea here to solve the problem. And that's this. We pre-compute everything. That's a very elegant solution and idea. Just here, that's what we do. We use the fact that we only need these 61 numbers. The Grundy numbers of from 0 to 60 or 1 to 60. So I calculate everything and then I copy everything that I calculated in my code. This method is called pre-compute. See, I first calculated everything, I outputted it, I copied and pasted in my code, so I now have it in OAuth1. I use the fact that there are only 60 numbers, so I can output the Grundy of all of them. I can wait for 10 minutes till the Grundy of everything will be calculated. I can copy it and paste it in my code, and then I use it. See in x, res x are equal to g of x, and then at the end, if res was non-zero, say out no, otherwise say out yes. And how do I calculate it? As I said, I just commented the part that I used to generate this. This is a very nice idea. This is a very nice trick to solve a problem. You just generate these numbers, copy it in your code, and then use it. You just need to generate it once. You just let it run once for several minutes, And then once you had it, you just print it. I just printed everything I needed and just I copied and pasted it the output. And in order to calculate that I just use bit mask. I just have some x and mask. These are ints, but ints is it is defined. I have defined int long. So these are long actually. And then I say that, okay, how many do I have and what is the mask of the numbers that I used? And I let it run, I copy and paste it here and use it. This method is called pre-computes. And this way you can solve the last problem in the contest today. Yeah, it doesn't have memory limit. There are only 60 numbers. So I'm saving 60 numbers. Yes, exactly. I only need the final Grundy without bitmask. Yes. At the end, I only need the Grundy number of those 60 numbers for the piles. I store all of them and I'm done. And this way I can get accepts on this problem. So that was the elegant idea of this problem. You can do this trick. You just do a trick. You just calculate it once, copy and paste it, and you just output it each time. Is it clear? If it is clear, put a plus in the chat or use the emoji. Otherwise, let me know if you have any questions. So, okay, I guess that there are no questions. Okay, so if it's okay, if you completely understood everything, I can maybe now answer the questions that you asked in the chats. Like how to master in DSA. Well, basically there are several good resources like Uselful guide, etc. You can also see the topic streams that I have in this channel. They are designed for you exactly. They are designed for you to use it and to learn the things that you need to know in order to have a good rating in Codeforces. And as I told you, I'm planning to make a course as well. If you want, you can tell me here that's what do you want me to make course about. I had it in my Telegram channel and most people talked about DP. So probably I make a dynamic programming course soon. But if you had other ideas as well, you can say that. And we can say that, how can we do this? But as I said, there are several challenges. There are some equipments that I need for a course. And I'm also talking to an editor. And the most important thing that I'm thinking about and the solution that I was thinking about was this. Well, I talked to an editor and they're talking like they're gonna get like the rate that the best rate that I could find was like $50 for 15 minutes of video. And one issue is for that is the budgets to make the video. And as I said, for that, I made some source so that you can donate if you want to support my work and you want me to continue doing this and also make the course. If you want, you can use that. You can find the link in the description below. As I said, no one has to do this at all. This is completely something that if you want to do. And I know that many of you just need to learn from here and you're not in a situation to help anything. But if you are in a situation that you want to help, you can use this link to support the work. And I'm telling you that it's just if you can. And yeah, course on how to deal with problems that look stupid, like IOI 2024 question 3. Course on interactive would be amazing. DP course on data structures. Okay, what else? And also if you have other questions, you can let me know as well. So I think that so far you can also talk about it in the Telegram channel or Telegram group as well. Most of the people who said ideas were talking about dynamic programming, creativity and brainstorming. Yeah, sure, I will think about all of them. That is like the most important course. I can also make general courses as well, like starting from the beginning to the end. But I was thinking to first started a smaller course. So if we want to start from a smaller course, probably dynamic programming is going to be a good thing. But you can also give me ideas if you want anything else that can help you better. Okay, good. And guys, also, if you liked this live stream, you can also support me by inviting others to watch the topic streams as well and sharing it with your friends. Again, that's something that you don't need to do, but if you do that, I would really appreciate that. And I plan to make it more structured and have the topic streams on Fridays each week from now on. And I hope that there won't be any issues, unless, for example, there will be some contest on that day that we have to stream the contest, etc. So the next contest is in 4 days, and the next scheduled contest is in 3 weeks, which is a lot. But yeah, I hope that I stream these contests. I will try to stream all the contests now that I'm back, like what we were doing 2 months ago. Yes, I try to stream all of them. I try to get back to how we were doing 2 months ago. Okay, do you have any other questions or comments? I will also put a vote in Telegram channel on how do you think about this stream? How was it helpful? You can rate it, or you can give me comments, give you your honest feedbacks, and I will try to use them to make the next streams better. Only CF or lead code. Yeah, I try to stream lead code contests as well. We have a lead code contest, I think, on Saturday nights, our nights. I'm stuck at specialists, how to become experts. Yeah, we can definitely do that. I will think about that, and I will talk more to you in the next streams and also in the Telegram channel as well. And there were some problems that we didn't solve today. I just solved the last problem of the contest. If we can, I will solve it in the next sessions if we had another session on game theory. Otherwise, you can also read the editorial as well. But I solved the hardest one, which was more challenging. But the rest of them, I hope that I will solve them. We have another session on game theory as well, because game theory still has some other topics that can be covered as well. Some other very beautiful things that can be covered as well. And I can solve the problems then. But so far, because the stream was on for around 3 hours now, I think we should finish it. But I will see you next time. Yes, 3 hours. We had the records. We never had the stream for 3 hours. It was at most 2 hours. Okay. div2d is becoming hard for me. Any tips? Solve a lot of div2ds, to be honest. My honest response is this. Just go to the previous contest, bring div2ds and try to solve them. Especially, I mean, the best method that I tell people to increase their rating is to solve problems around your current rating. That's what I believe in. That's what I believe really helps you to increase your level and increase your Codeforces rating. Okay, so thank you guys very much for attending the stream today. I'm so happy to seeing you again. I'm so happy that we had this session. I hope that we will have it on a schedule each week from now on. See you next time, guys. Thank you.